Hi guys, my name is Blake and I'm really excited for today's video. It's going to be part 2 of the series. The initial video was just the background of kind of firearms. This video we're going to be using the initial pressure in the chamber to solve for the uncorking pressure at the muzzle, which is useful for silencers, suppressors, muzzle brakes, compensators, and everything in a firearm design. So I hope you guys really enjoy this video because I love to nerd out a little bit. So we dive into it here. The assumptions we made in the beginning, I'll just go over them again, is we're going to use the cartridge dimensions, sorry about that, as a cylinder. So we're going to say that there is no lip here to the shoulder. And we're going to model this as a soda can at 20,000 and 55,000 psi. How I got those pressures was kind of the chamber pressure for the subsonic, 18.2, let's say, and for supersonics, let's say 55. And these are two examples here. This bullet is 110 grains, this is like 225 grains, so over double the weight. It goes less than half the speed though, and it's also less than half the pressure. So what we're going to do as well is we're going to use my calipers to measure the area of this case and model that as that soda can that we talked about. We're going to say the interior is 1.36 and 0.35. So we're going to use the stress equation here, a little closer here, which is just pressure, pound, what you're used to is pressure, pounds per square inch, which is the area, force over area. We're going to have a changing pressure, but the same force throughout. We're going to assume that there's also no more gunpowder burnt after the initial firing. So the area is going to change as we get more area. So we're going to assume that this here, when it fires, and then we're going to stack how many of these, in volume wise, on top of each other. I'm not going to calculate that, but you could think of it like that. So it's going to get more area, but the force is going to stay the same. After that gunpowder is burnt and turned into gas, there's no more being imparted on it. This is from yesterday. So 20,000 psi, we need to calculate the area of the case, and 55,000 psi for supersonic. We're going to calculate the area of the barrel, and after we know these, we can plug that back into the pressure equation, and the area of the barrel plus the area of the case is going to be the total area, and we'll solve then for the pressure at the muzzle, which we'll call the uncorking pressure. Just going to go over what I just said right here. This page will be real quick. Same force throughout, but so this is force, this is area on this axis. Same force throughout, but the area is changing. So we can solve then for the pressure at the muzzle knowing the force in the beginning. 20,000 and 55,000. Model that as a cylinder, 1.36, 0.35. This is the surface area of a cylinder. The radius would then be half of that, which is 0.175. The area of the case is then 1.69 inches with 55,000 and 20,000 chamber pressure. That leaves us with this much amount of force. Won't even try and say it. It's a lot. Feel free to correct me if I'm wrong too on any of this. So with that amount of force in that much area, what would happen if we were to use these same numbers but then add in more area? So we're going to add in the area of the barrel, which is 10.5 inches plus 0.3 inches wide. Same equation. Leaves us with 10 inches about square inches on the area of the barrel. So the total area is then going to be 11.72 inches. With that pressure at the top, or the pounds of force at the top, we're going to plug that into the force. And that's going to leave us with the uncorking pressure at the barrel, at the muzzle. And that's going to be with the supersonic round almost 8,000 psi, and then with a subsonic round, almost 3,000 psi. So that's a lot. So if you were to have any muzzle devices or anything like that, that means that there's going to be a lot of gases coming out of here, pushing in certain directions. And that's useful for design. So we can even measure these ports and calculate the forces on these. As well as if we had some piping, I just have a bunch of random piping here that I'll show you in a second. Let's say this is 1.25 inches, this is a 12-inch long, like rolling pin. Won't necessarily be strong enough, but I'm just going to show you an example here. So we have that 12-inch by 1.25 inches, which leaves us with the radius. And what if we were to add those areas together again? And that would then leave us with that much area in the let's call it a suppressor now, silencer. The area total is then the initial area of the barrel, case, suppressor, leaves us with that. And that then leaves us with a supersonic has this much pressure at the end of the suppressor, and a subsonic has this much pressure at the end of the suppressor if all gases are theoretically trapped within it, and slowed down. That's another assumption. And so that just shows us that we need to, what does that show us? It shows us that if we're running 300 blackout supers in a 10.5-inch barrel, that if we have a silencer that's, 1.25 inches and all this stuff here, it doesn't matter, I guess. If we have a suppressor or not, the uncorking pressure is going to be between 8,000 and 3,000, depending on what load we're running. And then if we were to design something, it would need to handle these pressures. And at the end of the suppressor, if we were to have these dimensions, it would be this. And this pressure significantly drops, and that's what helps reduce the sound and what we hear. And so what really material handles this? So that we definitely need something that will handle at least 3,000 or 8,000. And so if you were to go to something like McMaster car, this is my welding blocks, if you're really curious where I grabbed this stuff from. I have a bunch of stuff here. So obviously, you know what I mean. And if we were to go over to something like McMaster car real quick, and that's pretty much the end of the video. I'll go into more pressures and stuff later for the muzzle brake, but I thought that this would just be a good intro. Lower this. So if we were to go to McMaster car, where I ordered that stainless steel tubing from, this is 316 stainless. .304, 316, and that was 1.25 inches. We would see how much pressure this is rated for. So I don't even need to calculate the hoop stress. This is just what they say it's rated for at what temperature as well. 1.25 inches, it was the thicker stuff, so 3,200 and 72 degrees Fahrenheit with a max of 1,500. So you can kind of just see how things are designed, and I thought that'd be really cool. So thanks guys, I hope you enjoyed it. Feel free to subscribe for part 3.